Okay. So hi everyone, welcome to GROOT, another week. So today we'll be hearing from Georgy Luke, who will be telling us about invariants of colored links. So please take it away, Georgy.
Yeah, thank you. Good evening from my time zone. So basically, my work is on node theory. Particularly, what I was trying to do was construct some colored link invariant. So I came up with a notion of idea called multi-quandles, similar to the idea of quandles. So I will try to explain things from the basics of node theory. So as I have been told. So I don't think like it would be a hectic thing to understand the talk. Okay, let me start. So I will just start with the definition of a node. By node, we mean a set of points in R3 which is homeomorphic to S1, the unit circle. And by a link, we mean a disjoint union of nodes. So if L is the link, it's disjoint union of nodes Ki's, and we call Ki to be component of the link. And when we say two nodes are equivalent, say K1 and K2 are equivalent if they are ambient isotopic. Ambient isotopic is basically any kind of deformation we can do on a node, bending, twisting without breaking the node. Mathematically, we can define the ambient isotopy as an isotopy from R3 cross 01 to R3 such that h of K10 is K1 and h of K11 is K2. So it's basically deformation of nodes in the space without say breaking the node. And then by a diagram of a link or a node, it's a representation of the node or link by projecting it onto the plane. So we project the node onto a plane, and then the 2D picture, what we get, we call it a diagram. There are certain things hidden, but then for simplicity, I define it like this. Yeah, and then there are some classical moves on the diagrams of nodes which we can do very locally, which are called ready-master moves. So the classic moves in node theory. So the R1 move is, which is ready-master 1 move, is basically untwisting a twist into a straight arc. So it's a diagrammatic representation of a twist. So it's the projection of the twist onto the plane. If we untwist it, and then we get a straight arc, and vice versa. There are two kinds of this twist. That's R1 move, and R2 move is basically so sliding of one strand over the other, and vice versa. And R3 move is sliding a strand below one crossing, and vice versa. So the classical theorem in node theory is the following theorem. We say two nodes are ambient isotopic if and only if let's say nodes or links, they are ambient isotopic if and only if their corresponding diagrams are related by a sequence of ready-master moves. One direction, the converse direction is easy actually. The two diagrams of two nodes are related by sequence of ready-master moves. They are ambient isotopic because all these ready-master moves, like whether it's twisting and then twisting, or like sliding, which happens in R2 move, or sliding the strand below or over a crossing, all these are deformations in our space R3. So as I have said earlier, it's nothing but an ambient isotope. But then proving the forward direction, it requires some work. as it's a classic theorem and it's not what we are focused, I leave it as a fact. And then I move to the definition of quandles. Quandle is a algebraic object similar to group. It's a set with a binary operation del, which satisfies three axioms. The first axiom is axiom of idempotency. X del X is X for all X in X. And the second condition is if I define a map beta Y from X to X as beta Y of X is X del Y, then for every Y, this map beta Y should be invertible. Third axiom is axiom of right distributivity. That is X del Y del Z should be X del Z del Y del Z. Yeah. Moving on to so we have link diagrams, and then by using our idea is to not our idea the in literature this knot invariants or link invariants are determined using quandles. So I'm explaining how it's done. Given a node diagram or a link diagram, we color, we kind of label the diagrams, arcs of the diagrams using a given quandle X. So it's called coloring of a link diagram D by a quandle X. So it's a function from the set of arcs to X such that it satisfies certain crossing relations at each crossings of the diagram. By arcs of the diagram D, so we mean these lines which starts at a crossing and it ends at another crossing. So this arc, it starts at this crossing and it will in a diagram of a link, it will end at some other crossing. So those are arcs. And then the coloring of a link diagram D by a quandle, it's a function. Given a diagram D, we consider the set of all arcs in that diagram, and then we map, we consider a function from that set of arcs to the quandle X, such that it should satisfy some relations which we call the crossing relations. So the crossings could be of two types. It could be a positive crossing or a negative crossing. Positive crossing is as shown illustrated here. So this is the overstrand and this is the understrand. So if the understrand, the incoming strand of the understrand passes from right to left of the overstrand, it's a positive crossing, and otherwise it's a negative crossing. So for a positive crossing, if the labeling by quandle, if the overstrand is labeled by Y and the incoming strand is labeled by X and the outgoing strand is labeled by Z, the crossing relation is that the Z should be equal to X del Y. Similarly, at the negative crossing, the crossing relation is Z is X del inverse Y. So this del inverse is defined. So we were saying when we define the quandles, the second axiom was the map beta Y should be invertible. So actually when I say X del inverse Y, I take it to be beta Y inverse of X. Beta Y is inverse, beta Y is invertible, so I can consider beta Y inverse, and beta Y inverse of X, I define that to be X del inverse Y. In mind. So moving on to one important theorem which states which describes one kind of link invariant. So this set of colorings of a link diagram D by a quandle X, if we consider the cardinality of this set by fixing the quandle X, then it will be link invariant. So by the classical Reidemeister theorem, to show the cardinality of set of colorings of a link diagram D by a quandle X is link invariant, it's enough to show under the Reidemeister moves, the cardinality of the set remains invariant. So it's easy to see. In fact, there are similar theorems are coming in the presentation. So I will describe the proof of similar theorem. So from there, the exact same proof holds here also. So a dichromatic link is a link whose components are labeled by two colors. Like each component is labeled by one of two colors, and all the two colors are used to label the components of the link. So the two color we usually represent as 1 and 2. And a dichromatic link can be represented by a dichromatic link diagram, which is a classical link diagram with labelings on the diagrams indicating the color of the corresponding components. See, for example, I have drawn some dichromatic link diagrams. These are 3 rings which are interlinked, and we project it to get the diagram. And then this 1, 2, 1 indicates the color of the component. So this first component and the third component have same color, whereas the middle component, it's have a different color. Similarly here also, 2 colors are used and each component is colored by 1 color. And here when we say 2 dichromatic links are equivalent, if as links they should be ambient isotopy, and the isotopy should preserve the orientation as well as this labelings that are the colors of the components. Then we say those dichromatic links are equivalent. So in the literature, so the notion of diquandles are defined to construct dichromatic link invariants, as there are quandles for constructing link invariants. So a diquandle is again a set with 2 binary operations, del 1, del 2, such that x del 1 and x del 2, they individually form quandles, and they should satisfy this right distributivity property. X del I y del j z should be x del j z del I y del j z, where ij could be 1 or 2. Yeah, for every x, y, z. Similar to the notion of coloring of a link diagram by a quandle, we have notion of diquandle coloring of a dichromatic diagram D by a diquandle X. So here it's a function which maps the set of arcs of this dichromatic diagram to diquandle X, such that instead of crossing relation which we have seen, some similar kind of relations holds at positive and negative crossing, which I will show now. So when we say dichromatic diagrams, the extra things are that some coloring of the components. So the arcs will get those colors. So here the over arc have the color J, and then the under arc have the color I. And furthermore, it's a positive crossing. So and if Y, the over arc is labeled Y, incoming strand is labeled X, and the outgoing strand is labeled Z. Here the condition is Z is X del J Y, where J indicates the color of the overstrand. Similarly, at the negative crossing, Z should be equal to X del J inverse Y. This del J makes sense. So as we have seen, diquandle, there are two quandle operations, del 1 and del 2. And then similarly, the arcs have two colorings, 1 or 2. So it makes sense. Yeah. So all those functions that satisfies those relations is a diquandle coloring. So similar to the previous case, we consider all the set of diquandle colorings of D by X, and then its cardinality forms a dichromatic link invariance. Again, the proof is similar to the previous case, and then one more similar theorem comes up, and then there we a general case comes up, and there we give the proof. So it's actually the generalization of this theorem. So basically, so from here my work starts. So it's actually motivated from the dichromatic colorings and dichromatic links. So in literature, there is this notion of chromatic links, where the components of links are colored different in arbitrary ways. In dichromatic case, it was just two colors, but generally we can have any set of k colors. So a k colored link is a link whose each component is colored by one of k colors, and all of the k colors are used to color the link. And similar to this dichromatic link diagram, we have k colored link diagram, which is a classical link diagram with the color labelings of the components denoted by entries from the set 1 to etc. up to k. And here also we say two k colored links L and L dash are equivalent if there exists an ambient isotopy from R3 cross 01 to R3, which takes L to L prime with the condition that it also preserves the colorings of the components as well as the orientation. So similar to classical knot theory, we could talk about colored Reidemeister moves. It's basically the Reidemeister moves, but then as in the case of colored diagram, we give the colorings to the corresponding arcs corresponding to the color of the components of the colored link. So here the twist has the coloring I. Similarly, by deformation, the coloring won't change. So it's again have the coloring I. Here also the two strands, they might have different coloring I and J. After the after sliding also the color should not change. Similarly, the Reidemeister move, third Reidemeister move, here also the coloring won't change. Excuse me, give me a second. Yeah. And here one thing to note is that this these are moves are local Reidemeister move. So so since they are local, the labelings at the end should not change. This end and this end are actually the same. it's labeled y del k z. This is also labeled y del k z, and this stand is z, so is here. So here we see, but this stand and labeled as x del j y del k z here, but it's x del k z del j y del k z. So we define the notion of k quandles so that these two are the same. In the case of dichromatic rings, actually these two things were the same. Let's see here. Here we have said x del I y del j z is x del j z del I y del j z. So to construct a theory satisfying such that it satisfies this, that was my aim. So yeah, before going to that, there is this generalization of Ready-Meister theorem. Two k-colored rings L and L dash are equivalent if and only if their corresponding diagrams are related by colored Ready-Meister moves. So again, the converse direction. No, actually, the forward direction. If two colored rings L and L dash are equivalent, first of all, they are ambient isotopic. So by classical Ready-Meister theorem, they are related by Ready-Meister moves. And then giving back the colorings to the arcs, the color is corresponding to the color of the components of the link. The Ready-Meister moves will get a color, and the stands will get a color. They are colored Ready-Meister moves. And the previous, the converse direction, again they are since they are colored Ready-Meister moves, there is a they are actually just deformation, and then it's basically ambient isotopy, and similarly the color should also be preserved there. So going to the definition of k quandle. So this is how I define a k quandle. It's a set equipped with k quandle operation. Say del I running from 1 to k, such that x del I forms a quandle for each I, and then the right distributivity should hold. X del I y del j z should be x del j z del I y del j z. For any ij belongs to the set first k natural numbers, and for every xyz. So we call such set multi-quandles in general without mentioning the number of underlying quandle operation. If k is not explicitly stated, we just call them multi-quandles. So some properties of multi-quandles which we have defined as follows. So x del I y del j inverse z should be equal to x del j inverse del I y del j inverse z. X del I inverse y del j z is x del j z del I inverse y del j z, and then x del I inverse y del j inverse z is x del j inverse z del I inverse y del j inverse z. So the proof for the first statement is as follows. So the right hand side of the first statement is x del j inverse z del I y del j inverse z del j z is equal to by the axiom of multi-quandle, it is equal to x del j inverse z del j z del I y del j inverse z del j z. So x del j inverse z del j z becomes x, and y del j inverse z del j z becomes y, because x del j is a quandle. So then applying del J inverse Z on both sides, we get our first statement. Here del J inverse Z get cancelled. And then we get the required, here it will become x del y, x del I y, del J inverse Z. And for the second statement, x del I inverse y, del J Z, del I y, del J Z, again by the right distributivity axiom of multi-quandles, it's just x del I inverse y, del I y, del J Z. So x del I inverse y, del I y becomes x since del I is a quandle operation. And then applying del I inverse y, del J Z, we get the second statement. For the third statement, we use the second statement which we have proved just now. So so x del J inverse is del I inverse y del J inverse is del J Z is actually by the second statement, it's x del J inverse is del J Z, del I inverse y del J inverse is del J Z. So x del J inverse is del J Z by the axiom of quandles, it becomes x, and then y del J inverse is del J Z again becomes y, and then applying del J inverse Z on both sides, we get the required statement. So some examples of multi-quandles we give. 1 second. Okay. Yes. So we are here, right? So the example is x is a, let x be a quandle, then we define our multi-quandles as follows. So here del i's could be del or del inverse basically. So in that for then if we take del I to be del or del inverse, then the x del I coming from I1 to k forms a k quandle, because x del inverse is a quandle. If x del is a quandle, x del inverse is a quandle called a dual quandle, and then it satisfies the all this right distributivity property. So basically, these are the condition we require right distributivity property for the multi-quandle case. And then another example we can consider is that x del be a quandle, and then I define x del ijy as follows. So x del ijy is y operated over x ij number of times like this. So it's easy to see that x del ij is a quandle, and then also note that x del imy del im z is actually x del z del im y del z del in minus 1 z. So continue it iteratively. So we continue it like this. What we get will be x del in z del im y del in z. Each time this index will start reducing, and here it will start increasing by 1. So this is the right distributivity property we require for the multi-quandle field. So x del ij, j running from 1 to k, it's a k quandle. So the there is a quandle structure over R. So if Tj not equal to 0, x del Tjy is defined to be Tjx plus 1 minus Tjy gives a quandle structure on real line R. So we take some finite k number of Tjs which are not equal to 0. Then they give rise to a k quandle structure R del Tj j1 to k. Basically a k quandle structure over the real line. So we could see it easily. X del Tjy del TL is TL of Tjx 1 minus plus 1 minus Tjy plus 1 minus TLZ, which is TL Tjx TL 1 minus Tjy plus 1 minus TLZ. But X del TLZ del Tjy del TLZ is again TLX plus 1 minus TLZ del Tj TLY plus 1 minus TLZ. So if we compute this, we get this, and then one can see that all the coefficients of x and y are the same, and the coefficients of z, some of the coefficients get cancelled, and the coefficient of z will be 1 minus TL only. So basically they would be equal, and then this forms a k quandle structure. Yeah, and then we define similar to what we have seen earlier. We define what is meant by coloring of a k color link diagram by a k quandle x. So it's again function from we define to be the function from set of arcs of a k color link diagram to k quandle x, such that it satisfies these conditions at a positive and negative 100 crossing. Positive 100 crossing, the incoming arc Z should be equated to a x del jy, where j is the color of the overstrand. Yeah, and y and x are the labels of overstrand and the incoming strand respectively. Yeah. So our theorem is like similar to the all previous cases. This set of all these colorings of a k color link diagram D by a k quandle is in fact a colored node link invariant, k colored node link invariant, which says that yeah, this is our results for what we have came up with. So under the k colored link equivalence, what we were just explained, that invariance is detected by this cardinality of this colorings of k color link diagrams by k quandles. So the proof is using the theorem what we have stated before. This theorem that two k colored links L and L dash are equivalent if and only if the corresponding diagrams are related by colored Redemaster modes. So to show this is in fact a colored link invariant. There is a typo, I didn't incorporate colored here. So to show this cardinality is a colored link invariant, it's enough to show under the colored Redemaster moves the cardinality of this set of colorings of a colored link diagram by a k quandle remains invariant. But then this is the case which we have seen. We have seen the diagrams Redemaster moves. So we can see before and after the Redemaster move, there is a unique coloring. This is the only way we can color the k-colored diagrams. So since there is a unique coloring of a coloring by a k quandle before and after the colored register moves, this cardinality of the set of colorings remains the same. So it's a colored link invariant. Yeah, now I will just, I don't know how much time I have. Yeah, I think
So
I
probably,
have.
I mean, at least 10 minutes. Yeah.
Yeah. So we have time. So I will just show some computations I have done in Python. Sorry, it's just that I'm a bit unwell, sore throat and all. So this is what I have done. So this is actually a 3 quandle. K is 3 here. So these are the operation table for 3 quandles. So this is the operation table for the quandle operation del 1. This is for del 2 and this is del 3. So in fact, computation by hand would be a bit difficult. So we have to use some programming language to show that this set 1, 2, 3, 4, 5, it's a 3 quandle. To show it's a 3 quandle, we individually we have to show which of these del 1, del 2, del 3 is a quandle, and then this right distributivity holds among these quandle operations. So actually, it's I have verified it. I'm sorry. Sorry. Yeah. So first, these are colored links. So these are the same links. If we just consider the underlying link structure, but then the coloring is different. So the first component coloring is the same for both the links, but the colorings of the second and third components are interchanged here. Yeah, so what I am trying to show is that in fact our invariant what we have just seen, the colorings, cardinality of colorings by a fixed 3 quandle will detect this difference. That's what I'm trying to show. So this is our 3 quandle, and then we label these arcs as W, X, Y, and Z. So for them to form a coloring, it should satisfy this crossing relations at all these 4 crossings. So it's basically what we have done. So to calculating the number of colorings, so we consider the tuple W, X, Y, Z. The crossing relations are basically W is equal to W del 2X. So here W is basically W del 2X. 2 is the coloring of the component of the overstrand. And then Z is X del 1 W. Here Z is this. X is the incoming strand and W is the overstrand, and 1 is the coloring of the overarc. Similarly, X is Z del 3Y and Y is Y del 2. These are the crossing relations for the other crossings. Similarly, for the figure in the right hand side, we just wrote the equations, and then with the help of programming language, I have calculated it, and it's basically the number of such colorings for the first figure is 23 and the second figure is 29. So which says that this, even though their underlying link structures are the same, as colored links, they are not the same. And then for the second colored link, I think it's called a Borromean ring, and for it also with the same quandle structure, with the same 3 quandle, the coloring comes to be 71. Then I have computed some more examples. So basically these are two links. So the first component is colored I, second component is colored J, and the third to be K. So any of these could be 1, 2, or 3, since we are considering 3 colored links. So here IJ, KL belongs to a set 1, 2, 3. So what I have done is, this is L10N107 by the node cataloging. So I have considered all the 3 colorings possible. So this tuple indicates the first entry corresponds to I, coloring I, second to J, K, L respectively. So these are the all combinations possible, and as 3 colorings, because all the 3 colors should be used. So we have detect this, there is some 5 or 6 equivalence class. This 307 is repeated 4 times, 433 is repeated 2 times. So like that, 1, 2, 3, 4, 5, 6, 6, 7. Yeah, at least 7 equivalence classes are there. So it's not, as the coloring changes, even though underlying ring structure is the same, they are different as colorings up to colored ambient isotopy, or as equivalence class as colored rings, they are different. And the L9 and 27, this figure, so there are only 6 kinds of 3 colorings. 1, 2, 3, 1, 3, 2, like this. So 77 is repeated twice, 125 is repeated twice, 95 is repeated twice. So which says that if the rings have coloring 1, 2, 3 and 1, 3, 2, they can't be ambient isotopic as colored rings. Similarly, so there are 3 equivalence class, 3 different sets of colored rings at least for sure. This is what I have done. And then the basic node theory part and quandles I have taken from this book of El-Hamdani and Sam Nelson. Yeah, and then the diquandle part is a recent article appeared in Journal of Node Theory and its ramification. Yeah, by all this, and so this K quandle part is the work what I have done. I'm elaborating a little more on that, which is not ready yet. Yeah, that's all. I think I'm on time.
All right, let's thank the speaker for a great talk. Feel free to unmute yourself if you'd like and clap, or use the clap emoji in chat. So I see at least 2, 3. Yeah, okay, lots of clap emojis. Great. Yeah, so does anyone have any questions? Yeah, you can feel free to just shout it out, or if you type it in chat, I'll keep an eye on that. But all right, so it seems maybe not. So in that case, let's give the speaker one more round of thanks. So thank you.